To realize tasks like obstacle avoidance in dynamic environments, both static obstacles and dynamic obstacles should be sensed and represented. Currently, two manners are used for representations in dynamic environments. The first manner uses traditional static maps, such as the voxel map, to represent static obstacles, and a separate detection and tracking method to represent dynamic obstacles. The limitation is that dynamic obstacles would cause trail noise in the voxel map. The association procedure in tracking is difficult, and only the trained objects can be tracked. The second manner is to use dynamic occupancy maps. Particle-based map is a promising dynamic occupancy map that draws recent attention. Current particle-based maps are grid maps. Particles with velocities are used to estimate the occupancy status and the velocity of the grids. The input is a measurement grid map generated by ray casting. This kind of grid map suffers from the grid size problem. Large grids lead to a low resolution that is unfavorable for path planning, while small grids increase the computation requirements and cause gaps and inconsistencies. In addition, desktop GPUs are required, and thus small-scale robots like quadrotors cannot run this map. Our work aims to generalize the particle-based map to continuous space and build an efficient map that can run with onboard CPU devices. In our map, the obstacles are represented by point objects with continuous states. Particles, updated directly with the point cloud, are used to estimate the states of the point objects. The flowchart below shows the procedures of our map. The input is the point cloud. Particles are generated and updated based on the point cloud. With these particles, we can derive the continuous occupancy status of the map, which can also be voxelized with an arbitrary resolution. Besides, we can estimate the velocity of dynamic obstacles and predict their future occupancy status. The core procedures are prediction, update, particle birth, and resampling based on SMC-PhD filter. The prediction procedure propagates particles with a constant velocity model. In the update procedure, inspired by the perspective projection model for sensors, we use a pyramid structure in the sphere coordinate in the camera frame to represent the FOV space and the occluded space. The map is also divided into pyramid subspaces dynamically. We demonstrate that under Gaussian assumption, the objects in the black dash box can be updated with only point cloud in the activation space. Then the particles in the view field can be updated efficiently. In the particle birth procedure, current works generate particles with random velocities, which can cause severe particle false update problems, especially for large-size obstacles. Particles with the wrong velocity can be weighted and cause obvious noise. Thus, we add an initial velocity module by matching obstacles in adjacent frames. Particles are then generated with considering Gaussian noise and random noise. To better model static obstacles, a mixture model using static particles is adopted. We present three forms for our DSP map for comparison purposes. DSP static map considers only static model and can rapidly represent the position of obstacles without considering velocities. The map with random initial particle velocity is also tested and is called DSP random. The map considering initial velocity estimation and mixture model is called DSP dynamic. In the resampling procedure, the map space is divided in voxel subspaces to maintain uniformly distributed particles and prevent degeneration. These voxel subspaces are also used to store particles. We first evaluate the efficiency of our map on different devices. When the size of the input point cloud is fixed, the update rate of the map is mainly decided by the maximum particle number. The particle number in our following test is shown in the table. Then we evaluate the velocity estimation performance. Two pedestrians walk with constant velocity or randomly in two groups. Compared to KM matching, differentiating method, and KM matching Kalman filter method, our DSP dynamic map outstands in all metrics. The mapping performance is compared with a popular static local map, called EWOC, and a state-of-the-art 3D particle-based voxel map, called K3-DOM, in different simulation scenarios using different resolutions. Here the resolution turns to 0.1 meter. Then we present the mapping result with DSP dynamic map in real world. Finally, we show some obstacle avoidance demos in dynamic environments with our DSP dynamic map.